the end here. Now, it's really easy for you just to believe me about why this is here. I really want you to understand why it's important we have one-to-one. Let's say, for instance, it was not one-to-one. If it was not one-to-one, that would mean there were multiple points over on this side, right, that go to the same point in R. If I tried to do the inverse, what would be the problem? Because if I started over here and tried to go back, why would that cause me issues? Well, I would start here, right? And I would have no idea which one to go back to, right? In addition to that, I know that in order for something to be a function, each element here can only map to one over here, right? I can have it going to 2. So the problem is, if it's not one-to-one, I don't know how to get back to my original point. So it's important that T be one-to-one for us, so that inverse function. The other property we really want T to have, I want to write it down. There we go. And something that we assume is true when we do a transformation. Now, assuming is very, very dangerous, especially in math, because a lot of times we make assumptions. What happened is exactly what happened when Hannah caught me like 3 days ago, and I wasn't paying attention, and I was just like, assuming it's going from one thing to another. It's awful. So when we assume, in reality, we want to be able to prove it's true, and as we want to assume, the function for T have continuous first order derivative. Now I'm using plural here. Why is it important that H has continuous first order derivatives? What derivative is H, the function that they're going to have? H is a function of u and v, right? So it's going to have partial derivatives for u and for v. It's important that both of those partials are continuous, and we're looking at only the first derivative for them. If this is true, if they have first order continuous partial derivatives, we say T is C1. Continuous on its first order partial derivatives. Which gives us all kinds of really important, really cool stuff that you will not understand until you take advanced math. And so if you're looking for why it's important, an advanced calc book, the actual advanced calc class book, would have really cool clues as to why it's so important. I'm guessing most of you don't really care about it though, so the important thing is we understand we want it to be one-to-one, and we want it to have those first order partial derivatives continuous. How can you check if the first order partials are continuous or not? You can pick the first order partials, right? And then what are you going to look for in them? What kind of things make the partials not continuous? What kind of things make functions not continuous? Denominator could be 0. You could have problems with the natural logs, the inside of it being negative, right? What else? Square roots. And there's one more that kind of I forgot. It's actually, when we talked about the denominator being 0, we kind of mentioned it. But, think about your trig function. Is tangent continuous? Secant, cosecant, cotangent? No, right? And the whole reason they're not is because when we look at something like cosecant, we have 1 over sine, right? The denominator could be 0. But so we also have to watch out for the trig function. Okay, so what I want to do is look at an example of a transformation. I want to see what we can do with it.
Is that kind of fault related to volume, to the volume, and the calculation? Is it related to separate fault?
Yeah,
okay.
It's related to everything we've done so far.
Because I'm just trying to lengthen.
Yeah, no, we're still in chapter 12.
Okay.
We're not yet, yeah. No, it'll wrap back in, I promise. Okay. In fact, it's about to wrap in right now. Because when I think about it, I think that brings up a better example than what I have here. So, for example, let t defined to be the two functions, x equals r cosine theta, and y equals r sine theta. What two variables am I starting with? What variables do I begin with here? Well, I know a transformation is going to take whatever I begin with over to x, y, right? So what variables do I start with here? What variables do I plug in to get x and y? Our theta. So one transformation we've actually already seen is the transformation that takes us from polar coordinates over to rectangular. Now here's the big question for you guys. Is t 1 to 1? That is, write it down. Does each r theta represent a unique xy point? I want you to think about it though. I want you to think about it. When I take an x and a y coordinate, is there a unique representation for it with r theta? No, right? There are multiple r theta combinations that will map onto the same exact x and y, right? Is everyone okay with that? Give me an example. No, okay. So the answer to this is no. Which means t is not 1 to 1, so does t have an inverse transformation? No. Yeah, it's just for the specific example of t, the specific transformation. How can we make it so that t was 1 to 1? We could restrict it, right? What would we have to restrict? We have to restrict theta. We might even have to restrict r. Why might it be good to restrict r as well? Think about what we can have. I mean, if I want to go 2 units that way, I can do r equals 2, or r equals -2 would reverse the angle, right? So in reality, both of these coordinates allow me to kind of get different ways of expressing the same point. So I might have to restrict one, I might restrict both, there are different ways to do it. But in reality, when I look at a transformation, one of the ways I can assure it's 1 to 1 is to restrict x, that is, restrict the points I plug in the beginning. That's okay? Sweet. Okay, so now let's actually do the example I wrote down. It's a really good example, though. I'm really glad you asked that one. Okay. Go ahead. Look at another one. We're going to look at t being the set x equals u squared minus v squared, y equals 2 uv, and we're going to go ahead and do that. We're going to restrict x. That is the initial set in the uv plane. S is going to be the set of all u and v, such that 0 is less than or equal to u, less than or equal to 1, 0 is less than or equal to v, is less than or equal to 1. What we want to do is sketch the transformed region. R. Now to do this, we need to think about how this is transforming over. Now I can do it point by point, right? But that's going to be awful because how many points are there on a graph? So I'd be screwed if I tried to do it point-wise, right? So what I'm going to do first of all, when I look to transform this, is visualize the original. That is, visualize x. S is my original, so it's in the UV plane, because that's originally what I had, right? What is S going to look like? Singular. Let's talk about Y. Taking all the caps off the markers. Okay, U is between 0 and 1, right? I'm going to come over here, I'm going to go from 0 to 1. between 0 and 1, so I'll go 0 to 1. And so in total, let's see if I can make this actually straight. Now, it's important that I drew solid lines there. Why? Because it's bounded. Now, we learned some vocab a while ago to describe this. If I actually include my boundaries, what type of set is this? A while ago. I think back in chapter 10, maybe. I think 11. Because it's bounded, it is a length-bounded set. It's closed. It is closed, meaning it actually includes its boundaries. It's really important. We'll talk about why in chapter 13. But for now, just believe me. This is x. And what we want to do is we want to take x and we want to transform it over using t to the xy plane. Now to do this, the easiest thing to do, because we actually include those boundaries, is to transform over our boundaries. That is, when we look to transform this, our boundaries will match up to the new boundaries. Right, so when we do a transformation, whatever this wall is going to map onto the next wall, and so on. Now to do this, we need to think about what our transformation actually says. We know that our transformation is x equals u squared minus v squared, y equals 2uv, and we have some restrictions, right? Let's look at the boundaries over here. Let's talk about this one first of all. I want to grab this swap. This boundary right here. What is the equation of that boundary? What is that boundary given by? V equals 0, right? Because we're in the UV plane, so it's going to be V equals 0. So we're going to start with one of our boundaries. We'll start with V equals 0. Now, I don't care about V, right? I want to talk about x and y. And so what I'm going to do is I'm going to transform this over. That is, V is equal to 0, which means x will be equal to u squared, right? And y will be equal to 0, right? Okay, I need to think about this really quick here. I know y is equal to 0. If y is equal to 0, could this be like a parabola or something? Could it be a circle? Could it be something funky like that? What's it going to have to be if y is always 0? It's going to have to be a straight line, right? As soon as I see this, I know this is going to be a line, right? The only thing I need to decide now is what is x going to be on this line? Well, to figure out what x is, I need to know what u is restricted between. When v is 0, what is u restricted in between? 0 and 1, right? Which means if x is equal to u squared, what is the smallest x could be? 0 if I plug in 0, right? And what's the largest it could be? 1. And so all I'm going to get here is that right there. So I get line y equals 0 with x between 0 and 1. Okay, same thing. We got one of our boundaries, right? Let's look at the next one. Look at this one right here. What is the equation of that line right there? It's u equals 1, right? I'm going to do exactly the same thing. I'm going to plug u equals 1 into my equation. That will give me x equals 1 minus v squared, and y is equal to 2v. Do we agree? Want to see where that comes from? Awesome. Suddenly it's not as nice, right? Why is it this is nice? Is y constant? No, y is changing, right? Now, I don't want two different equations for x and y.